Today we will discuss about isospin. Isospin, we know charge symmetry and charge independence of nuclear forces. As we know, nuclear force act on the nucleus, and nucleus contains neutron and protons. And we call neutron and protons together nucleons. We know the force act on nucleons is same for proton-proton, for proton-neutron, and for neutron-proton, and as well as neutron-proton. This is the charge symmetry and charge independence of nuclear forces, and almost equality of masses of neutron and proton. Neutron and proton have equal mass. This strongly suggests that the neutron and proton are same particle in two different charge states. What we are trying to call it here is that the neutron and proton are the same particle, have two different states. Mathematically, it should be therefore possible to treat them on equal footing. We can treat both equally. This is done by introducing a mathematical 3D charge space, which is we call isospin or isospace. Basically, what is isospace? Isospace is a space or a group of particles which act same under the nuclear forces. The common name given to neutron and proton is nucleon, which is a particle with isospin half. The two possible states of this particle are specified by the possible value of third component I3, that is half, which is assigned to proton, and negative half assigned to neutron. This is basically projection of isospin. We donate it by I3 or IZ. Isospin for nucleon is analogous to ordinary spin of nucleon, and I3 is isospin space is analogous to Z component of spin in an ordinary space. Here spin is not actually spin. Here spin is a quantum number. Properties of isospin. Uh, as we have discussed, the properties of isospin, a group of particles is said to have isospin if it contains number of particles, that should be 2l plus 1, are identical in their properties as far as the strong interactions or strong nuclear forces are concerned, except their charge. Here we do not compare the charges. We know the neutron have neutral charge and proton have positive charge, but for nuclear forces are same for them. Now here question arises why we assign I half to neutron and positive half to proton or nucleons. Why we assign the I value for nucleon is half. For any value of I, value of I3 or Z component lies between minus I to plus I. Therefore, nucleon exists in two charged states. Nucleons exist in two charged states. We want the value of I3. Therefore, here देख how हम इसको कैसे निकालेंगे. 2i plus 1 को इक्वल रखना है जितने नंबर ऑफ पार्टिकल्स है. न्यूक्लियॉन्स के अंदर 2 नंबर ऑफ पार्टिकल है, that is neutron and proton. We have 2, that's why we have right here equals to 2. Now 2i plus 1 equals to 2. We have to find out the value of I. Here plus 1 in this side goes with minus 1. Here it have 1, then divide by 2, we get 1 by 2. Okay, from this equation we have to find out the value of I. That comes out to be half. Now the value of Z component, that is minus I to plus I. Here we have half value of I, so we have two values arises, that is positive half and negative half. Here positive value goes to the highest charge state. Higher value of isospin assigned to the particle in higher charge state, यानी जिसका चार्ज ज्यादा होगा उसके I3 की वैल्यू ज्यादा होगी. हमें पता है न्यूट्रॉन का चार्ज 0 एंड प्रोटॉन का चार्ज +1 है, तो हम प्रोटॉन को I की वैल्यू ज़्यादा असाइन करेंगे. In negative half and in positive half, we assign the value of proton is positive half. As we know, there are two particles, we call them duplet. For three particle, we call them triplet, and for single particle, we call it singlet. Isospin family. Here a number of particles tell us about the family. If it have single family, we call it singlet. Just like eta mesons, omega, and lambda. 2i plus 1. Here this is a formula. 2i plus 1 equals to number of particle. In singlet we have number of particle 1. So I, it gives the value of I and I3 components 0. So these are hadrons and all three are isospin singlet. Which are those? These are eta mesons, omega, and lambda. These contain single particle in their family and have spin as 0. Isospin duplet. Isospin duplet, as its name suggests, duplet means two. Those particle, those family in which we have two particles. Here the same formula 2i plus 1 equals to 2. Solving this equation we get I half, here plus half assigned to proton, negative half assigned to neutron. Same for cation, that is K0 and K positive. Here K0 I3 की value plus half and minus half. Same is for chi. Now isospin triplet, three particles, gives the value of I1, 0 and -1. This particle goes to the charge. According to their charge, higher charge will have the higher value of I3. Quadrupole have four members that contains that. Isospin conservation. In strong interaction, total isospin is conserved. This law is violated in weak and electromagnetic interactions. Okay. Uh, Isospin is conserved in strong interactions, but it is violated in weak and electromagnetic interactions. The earliest evidence for isospin conservation in strong interaction came from the observation of charge symmetry and charge independence of nuclear force, as I discussed previous. Here it is a numerical problem. Proton plus proton both combine or collide give us the proton, proton and pion. We know the value of I3 here is plus 1 by 2 plus 1 by 2. Here it is also plus 1 by 2 plus 1 by 2, and its pion, its value is 0. I3 delta I3 conserved, but value of I does not conserve. I is equals to 0 is discarded on both sides because I is equal to 0 can't give I3 equals to 1. So this reaction is possible for I equals to 1. Similarly, for another, there are two another examples. The deuteron in its ground state had I3 0. Similarly, its helium in its ground state has I equals to 0. This reaction is not possible because isospin is not conserved. Uh, it is an electromagnetic interaction, as we see the example number 5. It is an electromagnetic interaction because here it contains a gamma radiation. The reaction may possible. In electromagnetic interaction, I3 is conserved but I is not conserved. Okay. These you can see this table. This table have all the forces written on the interactions. All three interactions are weak nuclear interaction. strong nuclear interaction, and the last one is electromagnetic interaction. In weak, all the forces except space parity, charge parity, strangeness, and isospin is not conserved. In weak, in strong, all the forces, all the lepton number, baryon number, strangeness, all these numbers are conserved in strong interactions. In electromagnetic interaction, all things are conserved except isospin. This table shows the various conserved quantity in different type of interactions. Okay, here we have another formula that is known as Gelman-Nishijima formula. It turned out that the electric charge Q of particle uh, in terms of ratio of particle charge to the electric charge, the isospin projection I3, the baryon number B, and the strangeness S are conserved by the following relation. It gives us the main formula, that is Q is equals to I3 plus B plus S divided by 2. This formula is gives us the relation between the charge and I. If we know the isospin of the particle, we can calculate the charge. Similarly, if we know the charge, we can calculate the value of I. For example, high prons charge is equals to -1, I3 is equals to -1 by 2, baryon number 1, and strangeness number -2 for chi minus high pron. And this formula satisfies the above condition. The Gelman and Nishijima formula related the four physical characteristics for any meson or baryon. This existence of such a relation suggests that there is a defined internal completeness of established description of properties of strongly interacting particles. For example, omega minus, it's we have value, we can calculate charge as well as I. Similarly for k kaons, the unitary symmetry of strong interactions, baryon octet. These are some particles, and it is a table shows that the particles and their baryon number, their strangeness, their sum, and their I3 component. Okay, consider a system of coordinates in which abscissa axis is a projection of isospin I3 and the ordinate axis is y is equals to b plus s. A quantity y is called hyperchain. We call that the baryons, and sum of baryons and strangeness we call it a hyperchange. On this plane, we all possible we position all the baryon with spin half. That is proton, neutron, lambda, sigma, chi. These 8 baryons with spin half form a hexagonal in the plane I3 y. These are those 8 particles. That's why we call it octet. In the next in the next video, we will discuss more about it in detail. Thanks for watching.